What does blockchain have to do with epidemics and gossiping? Quite a lot, actually. In distributed systems, and especially in blockchains, epidemic algorithms play a central role in keeping the network in sync. Inspired by how diseases spread in populations, these algorithms work by having nodes randomly infect their peers with new information, whether it's a transaction, a block, or a vote. This approach, called the gossip protocol, allows decentralized systems to achieve fast, fault-tolerant, and scalable data propagation, all without any central coordination. So it's an essential mechanism powering how blockchains actually work. Why blockchains need gossip? In a blockchain, thousands of nodes, often geographically distributed, must stay synchronized. Every time a transaction is submitted or a block is produced, that information needs to spread quickly and reliably across the network. But blockchains don't use a central server to broadcast updates. Instead, they rely on peer-to-peer communication, where each node shares what it knows with a few peers and they share it with others. That's where gossip comes in. So, is gossiping just a nice-to-have mechanism in blockchain? No, it's a foundational layer for many blockchains. Gossip protocols aren't the only way to propagate data, but they are one of the most effective in large-scale, decentralized distributed systems like blockchains. Here's why. There's no central authority. Every node is equal. Gossip enables organic information spread without needing a hub or coordinator. Nodes join and leave constantly. Gossip doesn't rely on fixed topology. If you can reach some peers, you'll eventually receive all updates. Gossip scales logarithmically with the number of nodes. Even in large networks, propagation remains efficient. Gossip offers multiple paths for the same data to spread. If some nodes are slow or offline, others continue spreading the message. Random peer selection makes it harder to isolate or attack specific nodes. Combined with cryptographic validation, gossip resists censorship and manipulation. So how it actually works? At its core, gossip is simple. A node receives a piece of new data, like a block or transaction. It selects a few peers and sends them the data, or just a hash or header. Those peers check if they've already seen it. If not, they accept and forward it to others. The process repeats until the whole network is informed. This can take different forms. Push-based, when a node proactively tells peers what it knows. Pull-based, when a node asks peers what they know. And hybrid, which combines both for efficiency and is the most common model. But it's not always used the same way. While gossip is foundational, each blockchain adapts it differently depending on consensus design, data model, and network performance goals. Taking a look at this table gives us more understanding on the differences in gossip protocol implementation among different blockchain systems. Solana uses a custom gossip layer called CRDS, Conflict Tree Replicated Data Structures, for validator info, and Turbine, a tree-structured mechanism to propagate blocks. Blocks are broken into shreds and sent over UDP in a fan-out pattern, enabling ultra-fast propagation with low latency. Ethereum's Beacon chain uses libp2p with Gossip Sub, a publish-subscribe model. Nodes subscribe to specific topics like blocks or attestations and form topic-specific mesh networks. This reduces bandwidth by only sending relevant messages to peers interested in the same topic. Bitcoin uses a simpler, more conservative model. When a node receives a transaction, it sends an inf message inventory hash to peers. Peers then request a full transaction if they want it. It's more pool-based, which saves bandwidth but propagates data more slowly. Avalanche blends gossip with consensus. It uses snow gossip where nodes repeatedly poll random peers to decide if a transaction is valid and accepted. If most peers agree, the node gossips it forward. This approach helps it reach probabilistic finality quickly. Polkadot also uses libp2p gossip sub, but integrates it tightly with runtime logic. Each transaction or message is validated before being accepted into the gossip protocol. Message propagation is topic-based and runtime-aware, offering modularity. Cosmos, via Tendermint core, uses custom gossip logic. It prioritizes consensus-critical messages like pre-votes and commits. Transactions and evidence of misbehavior are gossiped as well, but with defined priorities to ensure consensus isn't delayed. NEAR uses a custom hybrid gossip protocol built on TCP. Each block is broken into shard-specific chunks, which are propagated among chunks producers. Nodes gossip chunk headers and use pool-based logic to request missing parts. The gossip system also spreads transactions and block headers with built-in rate limiting and deduplication. But it's not all rumors and rainbows. While gossip protocols offer massive benefits like scalability, fault tolerance, decentralization, they're not without weaknesses. In fact, the same properties that make gossip protocols robust also open doors to unique attack vectors in blockchain networks. Let's look at a few key risks. Eclipse attacks. In an eclipse attack, a malicious actor isolates a node by controlling or spoofing all of its peer connections. That node then only hears from the attacker, allowing manipulation of what transactions or blocks it sees. This can disrupt consensus, delay blocks propagation, or enable double spending. Bitcoin is particularly exposed to eclipse attacks due to its pool-based gossip and lack of authenticated peer selection. In a Sybil attack, an attacker spawns many fake nodes to overwhelm the network or skew information flow. If gossip is not rate limited or peer scored, this can lead to degraded performance or manipulation of consensus votes. Ethereum 2.0's gossip sub addresses this via peer scoring, banning bad actors, and prioritizing high-quality peers. Without proper deduplication or rate limiting, a malicious node can flood the gossip network with duplicate or fake messages, exhausting bandwidth and compute resources. NEAR protocol and Cosmos Tendermint use built-in deduplication, and some networks limit gossip propagation using TTLs or proof of work on messages. Latency and delay attacks. By selectively slowing down message propagation or only forwarding certain data to some peers, attackers can cause forks, race conditions, or consensus instability. Gossip networks must be designed to handle uneven latencies gracefully. These risks remind us gossip networks must be validated, scored, and designed defensively to be secure. So, what you need to know? Gossip protocols are the backbone of most blockchain networks. They ensure everyone gets the latest data quickly and reliably. They're inspired by epidemics, with nodes spreading information like infections. Every blockchain uses gossip differently, balancing trade-offs between speed, bandwidth, validation, and security. As a developer, understanding gossip gives you insight into transaction flow, validation sync, and even consensus mechanisms. So next time you think about how a transaction you submit to blockchain ends up on-chain within seconds, remember, it's not magic, it's gossip. And just like a good rumor, it spreads fast.